Bow your heads, please.
Heavenly Father, we thank you for this day. We thank you for the wonderful weather after the Hurricane Matthew. I pray for all the people that were affected. I pray for the people in Haiti. I pray for people in middle of Florida. I pray that you protect them as they're rebuilding. And I thank you that the hurricane moved so that we were safe. And I pray that you'll help us to understand the science this week, Lord, in the name of prayer.
Amen. Thank you, sir. I don't know if you've noticed yet, but we are now going into a chapter where you won't need your calculator. Yeah, I know. It's weird, isn't it? But we're learning a bunch of really good chemistry theory. And it's going to be very helpful when you're doing actual chemical reactions. You'll understand better what's going on. I wish it had been taught to me this way, the way he does it when I first learned chemistry. I'd have understood it a lot better. So it's really good the way he's got it set up. Okay, so let's put our test away and let's go on to Module 4. I actually spoke to Jay Wiles over the time period we were apart because I thought I found a mistake, but I misread his question. I haven't talked to him in years. And when he called me, I go, "Do you remember me?" And he goes, "Oh, yeah." I'm like, "Oh, thanks. Okay." Not sure if that was good or bad. I've known him for probably 20 years. So, long time. Yeah, I know it is. Because you know me, I call with questions. Well, what do you mean by that? So yeah. Oh, yeah, I remember you. Yeah. Yep. Yeah, physical science, I called him for a lot of them because that was the first thing I taught of his. So I had a lot of questions. That's why they know me the answers in Genesis. Because I'm in the Institute for Creation Research. Same reason I call, how do you explain this, So they know, they have certain people they sick on me now. Like, talk to Frank Sherwin. That's the guy at Institute for Creation Research. He's a nice guy. All right, let's see. On page 97, we are in chapter 4, and we are looking at the modern view of an atom and their chemistry. And so when we learned about the Bohr model, and we learned about all that stuff, that was the models like the plum pudding model and those different models were what built up to the model that we have today. And somebody tell me, what's the name of the model that we hold to today? Very good. Quantum mechanical model. And I got harassed this week as I mentioned to my husband something, and my brother-in-law was there, and he goes, "You're teaching high school students quantum mechanics?" And I'm like, "Yeah, they can cope, It's okay. You guys are all right, right? You survived. Wasn't bad." Anyway, but I like the way Jay puts it out because he makes it piece by piece, and so it really is helpful. But we now hold to the quantum mechanical model. Notice it is not a fact. It's not even a theory. It's a model. And that's how we explain it the best we can because remember, no scientific theory even is 100% accurate. We have to do the best we can. This also fits in some information we had from the Bohr model because we're still using quanta, aren't we? Quantum is just the singular. And so the quanta, remember, was the amount of energy that it was required for an electron to absorb or emit when it was jumping from one orbit to another. And that's one of the big changes between the Bohr model and the quantum mechanical model is instead of having an orbit where it stays a specific distance from the electron, that's who I mean by it, okay? The electron stays a specific distance at all times from the nucleus of the atom. That was the orbit. Now in the quantum mechanical model, we believe there is an orbital, which is a distance and that the electron can exist somewhere within that distance and any cloud of area in that area, and so it changes the way we look at it. Now, why did we need the change? Because the Bohr model's math only worked for the hydrogen atom. Oh my goodness, and there's so many more things to deal with. So they knew that it wasn't just right, but we did the best we could with it, and so they had to come up with something better. And so before we go into the something better, let's do the experiment. So we have the interfering light experiment, and we need feathers and a bare bulb. What did we see there? Well, if it worked correctly, you guys had the advantage because the light bulb broke. But if it worked correctly, what you were supposed to see was with the card with the 2 slits, you just saw the light bulb and through 2 slits, no big deal. But when we used the feather, then what I noticed immediately was the multiple colors, the rainbow, and I thought, oh, that's so pretty. And then when I came back and read the book and it said you were supposed to see multiple images of the light bulb, I thought, I didn't notice that. So I went back and got my feather and did it again, and I was like, oh yeah, 3 light bulbs. And then when I got closer, they came together, and as I got farther away, they separated again. And so what we were supposed to learn from that experiment, which I don't know about you, but I'm enjoying these experiments. They're pretty fun. What you were supposed to learn from that experiment is about constructive and destructive interference of light waves. Remember that the waves, light functions as particles that move in waves. You already read the chapter, but the point is that this showed that it moved in waves because what we saw was where let's start with the index card. It says that it just was the black in between because it didn't go through these types of interference. But over on page 99, it tells us that at the bottom of 98, it says that where the waves line up to help each other, so where the top picture shows you that where the waves line up, these actually add up and make bigger waves, and these actually add up to make deeper waves. And so that would be constructive interference, where the waves are overlapping one another. And you will have to be able to identify what that looks like on your test. I already took it, so I'm telling you. Okay? Whereas if they were destructive, they interfere with one another. Now it's not additive, is it? You have a peak hitting a trough, and so they kind of cancel each other out, and you have destructive interference. And so that they destroy one another. When we look through the feather, we had both constructive and destructive interference. The extra images of the light bulb were due to constructive interference, and in the areas in between the light bulbs, the extra images were where the light was destructively interfered with, which I don't really understand all of that. I mean, if I sit here and really ponder it, I can get my head around it, but it's not like, woohoo, I got it type of thing. I just want you to know that. But it's neat. And then it says that where the blue waves constructively are interfered, you see blue light. Where the red waves are constructively interfered, you saw red light. I thought it was really cool that when I looked through the feather, there was the rainbow. You know, I just liked that part. I thought that was good. So I like colors. Can you tell? Anyway, all right. So then it said that in 1801, we had an English Quaker named Thomas Young, and this blew me away. Can you imagine in 1801 looking at a hole in your curtain that's going through and happens to go through 2 slits and noticing this interference of light and figuring out what it meant? Really?
We have trouble understanding what they're explaining.
I know! I mean, the idea that this guy could look at this and figure this out just is mind-bending to me. But anyway, I guess I'm rather simple. I'd have just looked at it and said, wow, I need to sew up the curtain. You know, or what bug is in it that's making it look like that? You know, I just wouldn't have thought of this. So it shows you here how he was actually looking at how the light was working through constructive and destructive interference, and the dark areas were the destructive interference areas, and the light lines were the constructive interference areas. And this experiment showed that light behaves as waves. Now, why was that important? Because Sir Isaac Newton had said that light behaves as particles, and part of the reason that people all accepted that as part of it was because it was Newton. Okay, because Newton was a very popular guy, you know, he was a very smart scientist, but part of it was because people couldn't explain how light would travel through outer space if there was no medium for the wave to bounce through. And that was a good question. And so they had a problem accepting it. Yet in 1801, they looked at this experiment and light seemed to function as a wave. Particles don't explain why you would see that kind of experimental result. And people could repeat this experiment very easily by taking light through one hole and putting it through two slits, and they could see this interference occurring. And so people started to accept that light moved as waves because of this. So they moved away from Newton's particles, they moved to Young's waves. Well, then Dr. Wiles suggests that photoelectric effect was a problem for the wave theory of light, because if you shone light on certain metals, they would emit electrons. And that seems to say that light is particulate, rather made up of particles, rather than being made up of waves. And so then Albert Einstein in 1905 did his relativity paper, and it required light to act as a particle. So now we've gone back and forth, haven't we? Newton said particles, Young said waves, Einstein said particles. So we just decided to trust them both, didn't we? And so now we accept that light is particles that move in waves. And that is just our theory of light. And that's way over on page 104. And we're going to go back, but look on page 104. It's called the wave-particle duality. And it's the idea that light, as well as many subatomic particles, have the properties of both particles and waves. Okay, so slide back over to page 100 again for me, please. The particles of light are called photons, and we believe that those are tiny packets of light that bounce along in waves. It's nice when you can compromise and everybody gets to win, right? And so that's the current theory of light. On page 100, we have the comprehension question. It says, number 1, 2 waves overlap as shown in the 3 pictures below. Which will have constructive interference, which will have destructive interference, and which one has something in between? Now, which one has constructive interference, where the peak, the crest matches the crest, and the trough matches the trough? C. So that would be constructive interference. Where would they cancel each other out? So we have a peak hitting a trough. B. So that would be destructive interference. And then A is somewhere in between. So it's just somewhere in between. That's our answer. Okay, then we get to Austrian physicist Aaron Schrodinger. And he had a brilliant idea, and he really did. He really, really did. After reading Einstein's paper, and he knew that the Bohr model only worked for the 1 electron of the hydrogen atom, and it didn't work for anything above that. And he thought, wow, I wonder if light is able to move as particles or as waves. I wonder if electrons can behave as particles or as waves. So really, that was pretty cool that he came up with that leap, right? I think that was pretty cool. I wouldn't have thought of it. And so he applied that information, and it mathematically worked, which is pretty cool when you think about it. And so when he analyzed the electrons as waves instead of particles, then he realized that they weren't constrained to orbits. That's where the idea of orbitals came from. And remember that the orbit kept the electron always at a very specific distance from the nucleus. And in the physical science book, he actually gives the example of a dog being on a rope that is frozen so that it can only be a certain distance all the time from wherever it's tied to, which is a really mean picture. But anyway, oh, poor dog, right? But that was the idea of an orbital. It was always the same distance. That's not true, excuse me, an orbit, not an orbital. Look on the top of page 101. That's the idea of an orbital. That in an orbital, the quantum mechanical model, the orbital is, rather than being a fixed distance, it's any place in this particular area. And if you look at under the picture, it says one way to imagine a spherical orbital is to think about looking for the electron at different times and then mapping out where it was found each time. The result would be a cloud of dots, such as what is drawn above. The red circle in the center is the nucleus. So it's more of a cloud, an electron cloud, the orbital. And we could kind of think of orbitals as a cloud. They have different shapes, but it's a cloud. Yes, sir?
Is this the same Schrodinger who came up with the theory of a simultaneous life and death?
I have no idea.
Paradox. Schrodinger's paradox.
I'd have no idea. You would have to look it up. I do not know. I'm sorry.
Okay.
Okay, let's see. I'm still on quantum. That's all my brain can cope with. All right, so then we get to the orbitals, or the electron clouds. And a single orbital represents a specific energy for the electron in an atom. I want to get to the parts that you need. So it first shows us that if the electron is in the whatever energy level it's in, we designate that with a number. So if it's a 1, then it's in the first energy level. If it's a 2, it's in the second energy level. It's a 3, it's in the third energy level. And remember, that means it's getting farther and farther out. The first shape that the orbital can take on is a spherical orbital, which we designate as an S. You like it? I built you one. And then we're going to spear it to show the p orbitals. Okay. You should have seen the amount of clay dough I went through. Okay. The first orbitals are spherical. So it's not a circle. It's it's a sphere. It's anywhere in that sphere. So it's anywhere in the ball. So we could look at the s orbital, come out of there. At the s orbital as being that the nucleus is in there and that the electron is anywhere there. Now remember, these things are made up of mostly empty space, but we're looking at the cloud right now of where it could be. And then when you get to the second energy level, so remember, each orbital can hold 2 electrons, no more, because they repulse one another. And apparently, I remember this from school, they had opposite spins. Okay, maybe that keeps them so they can stand to be in the same vicinity with one another. But then once you get this filled, and there's 2 in there, and no more can fit in there, then the next electrons have to go into the next one. And this should actually be a sphere, but I've cut it in half, so this is a cross section, okay? And so now you have the second energy level, and it's the 2s orbital. 2 more electrons can fit in there. But once you get up to the second energy level, now you can also have p orbitals, right? And the p orbitals, Andrew says they're the Popeye orbitals because they're dumbbell shaped. But the p orbitals can go in the x-axis, the y-axis, or the z-axis, okay? So that they'll be shaped like dumbbells in whatever direction they're going. Once again, you can get 2 electrons in each of those orbitals. And so by the time you get done with the p level, you can seat 8 electrons, can't you? 2 in the 1s, 2 in the 2s, and then you've got 6 in the 3p orbitals, right? Oh, so I guess that's actually 10, but it's 8 in the second. In the first energy level, you can get 2. In the second shell, the 2s would hold 2 electrons. Then the 2p, I know these don't look like dumbbells, but let's see if we can stab this bad boy. The 2p would go with the x-axis, and then the y-axis. Let's see if I can do this. Yeah, I'm trying not to. I'm trying really hard. Here we go. There we go. So the P can go, these dumbbell-shaped ones, girls, I used to like to call them bunny ears because they look like loppy or bunny to me, but, you know, with the guys, we'll just do the dumbbells. Anyway, bunny ears is nicer. So we have the dumbbell shapes, and so those are the p orbitals. Once again, you can fit 2 in each. So in the second energy level, you can get 8. But if you were filling everything, there's actually availability for 10, isn't there? 2 here, 2 here, 2 here, 2 here, 2 here, right? So that gives us 10. But in the second energy level, am I confusing you, Aaron? In the second energy level, you have 8 possible, okay? 3 p orbitals and 1 s orbital. Then when you go up to the third energy level, you would take cans of Play-Doh, but anyway, and then you get a bigger S, okay, a bigger sphere, and then you would once again have 3 bigger p orbitals. But now, once you get to the the third level, energy level, now you can have d orbitals, can't you? And the d orbitals, there's 5 d orbitals. And the d orbitals have differing shapes than these p's. And you know what? I'm just going to show you really quickly, so hang on. there's your 1s orbital, your 1s, and then your 2s, your 1s, your 2s, and your 3s. Okay, that shows you your, those orbitals. Your p's, once again, look like dumbbells that go in the three different dimensions of space, x, y, and z. Here's your d orbitals. And once again, they look like dumbbells to me, okay? Here they go here. They go here. Then you get a dumbbell with a donut. Then you get dumbbells going this way. Then you get dumbbells going this way. So notice that there are 5 different orbitals, and you can fill 2 electrons per orbital, so you can get 10 into the d orbitals. So everybody, I'm not even going to the F and the G, forget it. But I think that's what you're seeing down here. So if you just want to have a glimpse, that's how, and thank God we don't need to know all those shapes. But inevitably, when I teach this, there's a student that goes, what does D look like? And so I wanted to show you. There you go. Everybody happy? Okay, so, yeah, down here, see? Down here, those are F and G. So when I found it online, I thought, I bet you somebody's online that's got a shape thing. And so I found that, and I thought, well, I could show you guys that real quickly. So, okay. Thank you, Jesus, that we don't have to know that. Now, when I was, okay, let's go on. I'm on page 102. So he tells us on page 102 and 103, actually, he says that when we get to the 3 level, the 3rd level, then we add the d orbital. So now we have the s, we have the p, and we have the d orbitals. And he says when you get to the 4th energy level, now you add the, let me get it right. Excuse me, the 5th energy, nope, that was the 3rd energy level, you add the Ds. I was right, the 4th energy level, you add 7 F orbitals, so that's 14 new ones. And then when you get to the 5th energy level, you add 9 G orbitals. Thank you, Jesus, we don't have to know about those, okay? I don't know about you, but I'm like a happy camper that we don't have to know about those. Now, we were told here that Schrodinger did get the Nobel Prize for his work, and because it was amazing that he figured out how the rest of these electrons fit in there, and it fit the math. And then it gave a real neat quote of his that he was astonished that science doesn't answer the really important questions, and all of us as Christians go, duh. But anyway, that was mean, I'm sorry. But, you know, it's sad when people think that science is going to answer all their questions, and it can't. And I feel so sorry for Hawkins, but we'll just not go there. Anyway, so then turn over to page 104, please. And on page 104, oh, I forgot to tell you something. I told you that when you get to the 3rd energy level, which is here, I numbered them here so you could see, the 3rd energy level, that you got a 3p orbital, but notice it's down here where the 4 is. Well, the reason is because the 4s takes less energy to fill than the 3p does, so it'll actually fill up before the electrons will start going into the 3p orbital. So that's why this chart is shifted like that. Okay, I just want you to understand that. We'll come back to that in just a minute. On page 104, on comprehension check number 2, it says an electron is in the 2nd energy level. What types of orbitals are available in the 2nd energy level? Tell me, what types of orbital? S and 3p orbitals, very good. And how many total orbitals, that was the shapes, and how many are available to it? 1s and 3p's, right? So 4. Number 3, an electron occupies a d orbital. What is the maximum energy, the minimum energy level for it to have a d orbital? 3, energy level 3. You don't get to the D's until energy level 3. Okay, then it says, wait a minute, do electrons really behave like waves? Yes, they do. And it showed you there that if you had an electron gun and you shot it through 2 slits, you would get the constructive and destructive interference pattern just like you would with light. See, now once it was explained to me, I can understand it. So you would get the same thing. And so that's why they came up with the wave duality theory, that apparently light and subatomic particles behave both as particles and waves. We do not understand it completely, but the evidence seems to support it. Then we are told that the electrons will go into the lowest energy orbitals first, and that they only get 2 per orbital because they're repulsive to one another because they're both negatively charged. And that principle is called the Aufbau Principle. It's German, and it means building up, and it tells us that the electrons will fill orbitals starting at the lowest energy ones and then fill higher and higher. And so he showed you there how that worked with a carbon, but he also told us that chemists are very lazy, so they came up with the electron configuration to show you. So if we did carbon and it has 6 electrons, we know that the first 2 electrons will fill the 1s orbital. So we're going to get 2 electrons in the 1s orbital. Then you have to go to the next level up, so you've got the 2s orbital filled. But we still need 2 more electrons seated, don't we? Because we only have 4. So we're going to put 2 electrons in, 2 electrons in the 2p, and now if you add those up, you have your 6 electrons, which is what you need for a carbon, isn't it? And so that's actually how I was taught to do it in college. I went to Auburn University for the first 2 years, and I took all my freshman and sophomore chemistries there. And when I was in college, let's say they wanted you to do iron. Now let's say you had to do iron, and iron is 26. How I was taught to do it at Auburn, because I think they were torturing us, I really believe this with all my heart, is so iron is 26, all right, so I'll put here 26 electrons. So I'd go 1s2, 2s2, 2p6, so what have I got? 10, I still need 16 to go, 3s2, so now I need 14 to go, 3p6, so now I have 8 to go. But now I have it memorized that I can't just go to 3D. So I have to go to 4s2, and I'd add that up again, and I've got 10 and 10. So I still need 6 to go. Now I could go to 3D and put in the 6. And I would count those all up to make sure I had the right amount of electrons, and that's how we had to do it on a test, because that's how we were taught it. And then when I got Jay Weil's book, and he showed this other way, I thought it was priceless. If I'd had this information in college, I'd have been everybody's best friend. They'd all bought me pizza just so I showed them this. I'm telling you, his textbook, the other textbook that he wrote, I told students, take this to college. There's like 3 tricks in here in this book that you will be the most popular person on campus in chemistry if you take it. And I've had students call me back after and say, you were right, because this is one of those little tricks. So let me show you.